Hi all, this is Priyadharshini, working as an assistant professor in the Department of Artificial Intelligence and Data Science. Today we are going to discuss the topic called an important topic in the design and analysis subject called the important problem types. So let's discuss the important problem types in design and analysis of algorithm in detail. So in the limitless sea of problems one encounters in computing, there are few areas that have attracted particular attention from researchers. By and large, their interest has been driven either by problematic's practical importance or by some specific characteristics making the problem an interesting research subject. Fortunately, we have so many motivational forces. In this section, we are going to introduce the most important problem types: sorting, searching, string processing, graphical problems, combinatorial problems, geometric problems, and the numerical problems. These problems are used in subsequent chapters. So let's start the important problem types in detail one by one. So first one is being sorting. So sorting problem is to rearrange the items of a given list in non-decreasing order. Of course, for this problem, the problem is to be meaningful. The nature of the list items must allow such an ordering. As a practical matter, we usually need to sort list of numbers, characters from an alphabet, character strings, and most importantly, records similar to those maintained by schools about their students, libraries about their holdings, and companies about their employees. In the case of records, we need to choose a piece of information to guide sorting. For example, we can choose to sort a student record in case of an alphabetical order of names, or by student number, or by student's grade point average. Such a specifically chosen information is called the key. Computer scientists often talk about sorting a list of keys even when the list items are not records but say just integers. So the next problem type would be the searching. The searching problem deals with finding a given value called a search key in a given set or a multi-set which permits several elements to have the same value. There are plenty of searching algorithms to choose from. They range from the straightforward sequential search to a spectacularly efficient but limited binary search, and algorithms based on representing the underlying set in different form more conducive to searching. The later algorithms are of particular importance for real-world applications because they are indispensable for sorting and retrieving information from large databases too. For searching too, there is no single algorithm that fits all situations the best. Some algorithms work faster than others but require more memory. Some are very fast but applicable only to sorted arrays, and so on. The next problem would be string processing. In recent decades, the rapid proliferation of applications dealing with non-numerical data has intensified the interest of researchers and computing practitioners in string handling the data. A string is nothing but a sequence of characters from an alphabet. String of particular interest or text strings which comprise letters, numbers, and special characters. Bit strings which comprise zeros and ones, and gene sequences which can be modeled by string of characters from the 4-character alphabet ACGT, which is a finite automaton set. It should be pointed out, however, that string processing algorithms have been important for computer science for a long time in conjunction with computer languages and compiling issues. One particular problem, that of searching for a given word in a text, has attracted special attention from the researchers. They call it as string matching. Several algorithms that exploit the research nature of this type of searching have also been invented. The next type of problem is the graphical problems. So one of the oldest and the most interesting areas in algorithms is graphic algorithms. Informally, a graph can be thought of as a collection of points called vertices, some of which are connected by line segments called edges. Graphs are an interesting subject to study for both theoretical and practical reasons. Graphs can be used for modeling a wide variety of applications, including transportation, communication, social and economic networks, project scheduling, and games. Studying different technical and social aspects of the internet is in particular is one of the active areas of current research involving computer scientists, economists, and social scientists too. The next problematic type is combinatorial problems. From a more abstract perspective, the traveling salesman problem and the graph coloring problems are examples of combinatorial problems. These are problems that ask explicitly or implicitly to find a combinatorial object, such as a permutation, a combination, or a subset that satisfies certain constraints. A desired combinatorial object may also be required to have some additional property, such as maximum value or a minimum cost. Generally speaking, combinatorial problems are the most difficult problems in computing from both a theoretical and practical standpoint. The next algorithm or the problem type is geometrical problem. So geometrical algorithms deal with geometrical objects such as points, lines, polygons. The ancient Greeks were very much interested in developing these procedures for solving a variety of geometric problems. From simple geometrical shapes to triangles, circles, and so on. Of course, today people are interested in geometrical algorithms. It's quite different applications in mind, such as computer graphics, robotics, and tomography. We will discuss algorithms for these classical problems of computational geometry, that is the closest pair and the convex hull problem. The last and final problem type is the numerical problem. So numerical problem is another large special area of application. There are problems that involve mathematical objects of continuous nature. They are solving equations and system of equations, computing different integrals, evaluating functions, and so on. The majority of such mathematical problems can be solved only approximately. Another practical and principal difficulty stems from the fact that such problems typically require manipulating real numbers, which can be represented in a computer only approximately. Moreover, a large number of arithmetic operations performed on approximately represented numbers can lead to an accumulation of the round of error to a point where it can drastically distort an output produced by a seemingly sound algorithm.